All right, welcome to video 3 in this series on the resting membrane potential. This will be the last. We talked in the first video some introductory stuff. We talked about what's voltage. I think you guys probably got that. And then we talked about the equilibrium potential for ions and how that's generated, how much ions you have to move to generate a voltage. And we talked about the dependence of the equilibrium potential upon concentration gradient. We talked about the Nernst equation. Okay. Now we're going to talk about what happens when you move multiple ions, and which is closer to a real physiological situation. In reality, you never get membranes that are permeant to just one ion. I don't know of any situation where any physiological situation where that's the case. Okay. In reality, you are always somewhere away from the equilibrium potential for that ion, which means in reality that ion is always moving across the membrane. Okay. And we'll talk about how that can be right now. So we talked about equilibrium potentials. This is a table with typical ion concentrations inside and outside of a membrane. And these are typical physiological equilibrium potentials, okay? So the equilibrium potential for potassium is about -95. And that's roughly what you get when you have 140 on the inside and 4 millimolar on the outside. By the way, you should be familiar with these concentrations. You should not memorize them, but you should be able to recognize grossly abnormal. You should at least have a feel for them. But you don't need to really memorize them. You know, you just have to be familiar with the general concentration ranges, all right? So if you plug in those concentrations, you should get roughly -95. I haven't checked the calculation, but that's where it should come to, all right? So that means that if I make this membrane permeate to potassium only and let it flow, eventually I'll generate a voltage of -95, and that will stop the potassium flow, all right? For sodium, it's a little bit of a different situation because sodium's high on the outside and low on the inside. So it flows from outside to inside. So in the case of sodium, you get positive charge building on the inside, negative charge on the outside. You generate a positive voltage. And the more positive the voltage inside, the more sodium is repelled and kept from crossing this membrane, and eventually you generate enough voltage to where the sodium stops crossing altogether, and when you do that, you get something roughly +60 physiologically. So these are physiological concentrations of sodium. The Nernst potential for sodium, roughly +60. It's positive because you're generating a positive voltage on the inside instead of negative, which is what you got with potassium. So those are our equilibrium potentials for sodium and potassium. Now the question is, what happens if you have both, which is closer to a physiological situation? Now, what membrane voltage will you come to? Okay? Well, you have EK and ENA, and the answer is that if both, the permeability of the membrane to both is exactly the same, you get a voltage of -17.5, okay, which is exactly halfway in between these Nernst potentials. At that potential, you still have potassium. It's still flowing from inside to outside. You still have sodium. It's flowing from outside to inside, but the flows are equal and opposite. And because they're equal and opposite, you get no net change in the charge. And if you're getting no net change in the charge, that means you're holding steady at a steady voltage. And the steady voltage here will be halfway in between, -17.5. At -17.5, if I have the same permeability, that means that Vm minus Ek is equal and opposite of Vm minus ENA, because I'm halfway in between the two. And that means I have sodium current that is equal and opposite of potassium current, if I apply our old friend Ohm's law. Okay? All right. Great. Simple, right? Go halfway in between. Well, Not so simple. Because physiologically at rest, in pretty much all cells, the permeabilities aren't equal. Here I've added a column to our table. We have relative permeability relative to the permeability of sodium. So the permeability of sodium relative to sodium is 1. The permeability to potassium is 50 times greater than the permeability to sodium. Okay? So our permeabilities, that is our G's in our Ohm's equation, are not equal, like I assumed when I had minus 17.5. So now the question is, what voltage do you come to? The answer is found in the Goldman-Hodgkin-Katz equation. And you do not need to memorize this equation. You should just recognize the relationships in it. But you can theoretically calculate a membrane voltage. If you plug in all the parameters here, you have the permeability for potassium, you have the permeability, that's P, permeability for sodium, you have the concentrations inside and outside the cell. You can, in theory, use this equation to do the calculation. Right? A couple things about this equation. We're going to forget about chloride for the moment. I'm going to bring that back in a minute. Okay? So this is the equation with just sodium and potassium involved. All right? And notice if I cut one of those ions out, and for instance just make it potassium, that the GHK equation breaks down to the Nernst equation. Okay? And that sort of makes this fairly convenient. There's another equation that I actually like an awful lot that I describe in the notes. It's called the chord conductance equation. You can use that to do these calculations as well if you desire. You do not have to do them. I do not require that. But nevertheless, I think the GHK equation, I think it's emphasized a little bit more in board review books. So that's the reason I teach it. But it's important to note, if we cut it down to one ion, it breaks down to the Nernst equation. The membrane voltage will be equal to the equilibrium potential because you only have one ion flowing. And when that ion stops flowing, that means your voltage has come to rest. And your voltage will come to rest, therefore, at the equilibrium potential for potassium. That is the amount of voltage that you have to build in to stop this flux altogether, if it's just potassium, which of course is not the case typically physiologically. So here's our equation with just potassium and sodium in it, okay? And if you do a calculation with that, you will get something roughly minus 80, or you should, okay? It probably depends on what range you use in this table, all right? Instead of minus 17.5, you get minus 80. Now you'll notice minus 80 is really close to minus 95, really far away from sodium. Well, that kind of makes sense. Let's take a look at Ohm's law, all right? If Vm is minus 80, it's really close to minus 95. Minus 80 minus 95 gives you a fairly small number here, only 15, okay? For potassium. But the permeability of potassium, the G, the conductance term for this equation, is large. So I have a large number here and I have a small number here. Now if we take a look at sodium, minus 80 is really far away from plus 60. So minus 80 minus plus 60 gives me a very large negative number, equal and opposite. But my sodium permeability is relatively small. So in the case of sodium, I have a small G and a large potential difference. In the case of potassium, I have a large G and a low potential difference. The currents are equal and opposite where the voltage is really close to EK, because EK has a really large conductance element, okay? And they don't become equal and opposite until those parameters multiply out to the same number in the opposite direction, okay? So for sodium, low here, high here. For potassium, high here, low here. Put them together, you get the same current, equal and opposite. That's where it comes to rest. That's why your resting potential is closest to the ion that's most permeant to the membrane. In most membranes, it's going to be potassium, okay? All right. So let's talk a little bit about chloride. Now for sodium and potassium, these gradients, high inside, low outside, high outside, low inside, are generated and maintained by the sodium-potassium ATPase, the sodium pump, okay? And whenever sodium and potassium cross this membrane, the sodium pump pumps the ions back in the opposite direction. It actually generates a voltage as well, about 10 millivolts, which is why this minus 80 isn't minus 90. If you account for the sodium-potassium ATPase and its transport, this becomes minus 90, just for the record. It does generate a voltage. You're transporting 3 sodiums out for 2 in. So you're transporting a net positive charge out, and that lowers this number a little bit. Anyway, that pump maintains these gradients. All right? There's no pump for chloride. Chloride's not actively transported in most membranes. All right? So what does chloride do? Well, it moves, instead of generating voltage, it moves in response to voltage. Okay? So if my membrane voltage is minus 80, that means I'm going to take chloride and I'm going to shove it out of the cell, because negative charge repels negative charge. And what happens is my chloride concentration inside the cell drops. And it drops until I've generated a gradient here, so that my 2 forces are equal and opposite. I have an electrical force repelling chloride, shoving it out, negative charge here, and then I have a concentration gradient for chloride tending to make it want to re-enter the cell. When those 2 things are equal and opposite, chloride stops moving. Because chloride isn't actively transported, that concentration gradient will be generated such that when chloride stops moving, the membrane voltage and the equilibrium potential for chloride will be the same. So chloride moves until the equilibrium potential for chloride becomes equal to the membrane voltage. Okay? So it's the opposite of the sodium and chloride, where sodium and chloride are being actively transported and they're generating voltage. In the case of chloride, it's moving, and it's moving in response to voltage until its concentration gradient builds to the point where it stops moving. And at that point, the equilibrium potential for chloride will be equal to the membrane voltage. Okay, and that's the story with chloride. In the action potential, the synapses lecture, we'll come back to this, and we'll talk about chloride's role in the synapse, and it's relevant to this. Okay, bear with me. All right. So that's all I got. Thank you for your attention, and I'll talk to you when you decide to start the action potential lesson. Thanks.